here 10 years ago here. So it's really great. Right. So what I'm trying to bring you here is maybe a biased view, what I think is going on right now in the field, and trying to project ourselves where we're heading, where I think the field is moving, and what are the kind of topic of main interest. And that's the reason why I call this talk the next frontier. So let's try to see where we're going. So we all know what amazing result has happened, but what does it mean? Okay, so I will do that as a series of statement and trying to challenge maybe some elements there and show you why I think the statements I think are relevant, at least for me. Well, I think the first statement I would like to make, I think the universe has been generous with us. Because when you think about this number of planets where we have detected right now, nothing really was planned like that when we enter into the game. And one way to just see that is just to simply have a diagram when you just expose what we have measured, the simplest possible parameter we have measured on the many planets that we have detected, about 6,000 as of today, which for most of them rely on getting the mass or the minimum mass times sine I of the angle from radial velocity techniques. And the other one is getting the radius by the transit. This is the real data. There is no conversion here. It's really what you get when you extract all the known planet. And the color code is just used to identify the discovery, the first discovery. So it's red is radial velocities, blue is transit. Now, the reason why I start this way is because this picture is, in a way, fascinating because we have so many planets there. And this is why most of this, I mean, a lot of people here are working on that topic. But it's also very frustrating because the system we know the best, because we can go and visit the planet, is the solar system. And actually, clearly, when you look at all the planets, it's whether you use the mass, the period, and the size, we're really sitting in a category here, which is not exactly the one we can compare. So practically, most of the planets we have found, or 95% of them, they would be sitting within the orbit of Mercury. And doesn't really fit into the way we understand. Of course, we have category, the hot Jupiters, the super Earth, mini Neptune, all this kind of stuff comes in. But practically, I think it's a serious challenge that we are facing it. On the other hand, it's what I call the gift of the universe, because without this intrinsic diversity and the fact we have so many systems which are clearly different from our own solar system, I will not be talking in front of you. And I think the field will be just almost dying. Because these two techniques were the worst possible technique you can think about to find planet. And the worst of them is transit, because transit is missing most of the planet, most of the time. And what you can get of them is a glimpse for a brief moment. So all this, when you think about that, I think it's interesting because it brings the solar system in a kind of awkward situation. So to understand within this diagram, I mean, some of you are familiar with this kind of limitations. It's just some idea to give you what is happening here. This is about my translations of the situation we are in, which is quite interesting because practically the fact that we have so many planets which are clearly different from the solar system doesn't mean the solar system is special, because right now we have not been able to just detect it. And that's good to just remind us this, because from the very beginning, it was really the focus there is getting its directions, but clearly it's difficult. It's more difficult. Well, the transit always suffers from the statistics. So there's a limit beyond maybe 6 months, becomes really dramatically low, and you need so many planets to get one statistically. So it's almost no chance to do anything. And when you detect small system, well, you need many transits, so it makes your life easy when it's short period, more difficult when it's higher. And then, of course, we're looking at stellar objects. So the objects are not just a sphere. They're really practical, active object. And then clearly the photosphere is not something you can treat as a constant signal here. And all this makes this situation right now. So it's amazing discovery space, getting all these different categories, an amazing series of data, but clearly a lot of questions. We are here. And 30 years after, there's only one thing we can say we have learned about the planet. They are common in the galaxies. because when you run the number, there's kind of number that you can extract from these groups of planets. But they are common in the sense that the most common planets are not exactly the way we thought they would be, because most of these planets that we're detecting right now are called stars. That's the occurrence, typical occurrence you find in the literature right now about these groups of planets. There's a lot of debate on the specifics here, but I just don't want to go specifics. I just stay on the board, stay here. The planets that are most common in the galaxies are the ones nobody had imagined they would exist, because they are planets that practically will be sitting clearly within the orbit of Venus, and if it's not, in the case of Mercury. Of course, this is a very biased view, because the closest you get to this threshold detections, the more difficult it becomes. So there is this degradation of number of planets that happen when you get closer to this line. Anything on the left side can be detected, but get more and more difficult. And to cross this line is really even more difficult. So this is really what we're dealing with. But on the other hand, if you don't get obsessed by the solar system, it's great. We have planets on all masses, on all size, way more than we thought. There are clearly regions where the planet seems to be not very common, and people are addressing this in various ways. It could be formation related. It could be after formation, the impact of get too close to the stars and may have trouble with the stars and may evolving there. So there's a lot of very interesting elements that were not really thought at that. And of course, the formation mechanism has been now expanded. We clearly had to consider the fact that planet doesn't stay where it formed and they can moving around with the various mechanisms, which is still mystery. When you think about the hot Jupiter, everybody agreed migration may be playing a big role, but how do you stop the planet? And there, I think there is not really a clear understanding of this. So this is my first statement here. We have been really lucky. Now, we can turn this in the other direction. You can ask yourself, oh, are we special? Because the fact we're having this conversation today on the planet Earth, that seems to be unique right now, according to what we've done, does it mean is it has to be like that for life to pop up on the planet? Is it just a prerequisite, or it's just lucky? And we don't know that yet. But that's something I will come back, because that is one of the central points that we are talking about. Of course, anytime we get something like Earth mass, Earth size, we get excited. But we have to remind us that an Earth mass or size, when you have a one-day period orbiting the stars, it makes more a lava world than anything else here. So it's just something to keep a bit of perspective about what it is. Okay, that's my first statement. The other one is, of course, in addition to the diversity of this world and the fact that they are different from the solar system, there are still some common ground. You can connect these planets with the one of the solar system when you move to another scale, which will be the composition of the systems. We know very little, we have to admit, and we can be very gross in a way we do that, and we can produce this kind of average density. Average density is very poor information, practically, when you think about that, because there's many ways to turn around. This is not the most updated, so there have been one, but I want you to go through from people not familiar with that in the field. So this is really, let's say, the state of the art what astrophysics can do on planetary physics outside the planet, outside our solar system in terms of structure of the planet. Well, there are a couple of facts that we should feel very confident for us to go through. Well, we have planet that is clearly in the realm of the giant planet, but because they are so close to the star, they're not fitting exactly what we expect in terms of density regime. So density regime is built on the understanding of Jupiter is essentially made of hydrogen, and it's what it is, and you can produce the structure of Jupiter. It depends on the state equations there of the hydrogen, and most of the other giant planets we have, you see them above where you expect to have Jupiter standing above it, which means they are slightly inflated. The density is less. So the clear understanding of that is not very clear, but everybody would agree still this is fitting the structure of a giant planet. We do have some, and we can work in the detail here when they are a bit cooler, not hot, and then they tend to go down and settle down on this regime that is connecting Jupiter and Saturn, that level here, that describe a giant planet. So yes, giant planets are being formed, and that is already a very good news in a sense, because that was one of the main difficulty in the formation of the solar system, to understand how you can form a giant planet. So yes, we have the timing right, so we just have to work the way it has to happen. So this is a very interesting finding. Now, what is interesting here as well is when you go down the density, you are reaching the mass of Neptune here. Neptune doesn't fit at all the giant planet density. Well, we understand why. That's why we consider this called ice giants as a failed giant planet. Is essentially they never managed to accrete all the hydrogen in a similar way than Saturn and Jupiter. There's also good explanation for that when you run to the formations. So the timing has been slower, everything is different. So you can imagine you grow to your critical mass to attract hydrogen. By the time you reach this level, then the hydrogen is gone. You get a bit of hydrogen there, but certainly not enough. But you're getting also some other gas there that looks because of the low temperature, get you this feeling to get this icy giant, which actually they are giant practically in terms of structure. Now, what we do usually here is we're entering into this confusiongram, which a diversity of planets start to reach this kind of level of density when there is a lot of different ways to see them. So I don't want to enter into the detail here, but what I love to do is to stick in on the theory, only a theory, and add a planet that is just doesn't exist, which is in that case the blue planet here. It's a planet that will be entirely made of water. So why doesn't it exist? Because we know on the structure of the formation of the planet, you have to glue the planet and build up from the inside out. So you have different material, different structure of the material. You cannot get only water here. But it's interesting to give you an idea already where you sit, because you can use it as a comparison about the kind of planet you're talking about. This is the origin of this huge diversity of planets that are clearly going beyond Neptune. So you cannot explain all the planets we have beyond Neptune with a Neptune structure. It doesn't work. You have to find something else. It means you have to change the compositions, you have to change the size of the core, or you may have to argue there is less on that, more on that, and you can play with all of that. And you can play so much that you can stay on the same size than moving the mass even down to few Earth mass. So this diversity was really a shock at the beginning because nobody had thought it would be possible to do that. But we have to admit that the structure of the planet can be way more diverse as soon as you get down to some level, which when you think about the diversity of planet formation, should not be a surprise, because when you form the planet, you have to agglomerate and glue together all the solids you have. And depending where you're sitting, how you're doing that, what you call the solids. Solids could be, in most of the case for the giant planet, just the gas that is too cold to be in a gaseous form or in a solid form. This is why you have so much in the Neptune case, so much of the heavy gas, because at that time, at that moment in the formation of the solar system, they were not gases at all. They were just solids. Famous snow or icy form is too cold. So they are appear as solids, they're gluing together, the solids stick on the plane, they're all together, they're very close. They don't have to fight with the pressure. So you don't have to deal with this kind of expansion of the size of the disk and the vertical side. They're really, really thin, and they eat each other and they're building up. So of course, depending on you form the system, if you assume that you can form the system, you can form a planet at any location of the disk, you will be probing very, very different kind of composition. So it should not be a surprise at the end that we end up with a very difference. Because if you imagine any planet can be formed at any location in the disk, reach a mass of below Neptune, it's a kind of fast process. If you think it's kind of a process that happened in a natural way in the early stage, the first million years of a protoplanetary disk, of course, you will get a diversity of system. And if you add that, then the dynamic with the disk is going to mess up everything. Like you can shape all the positioning. That's what you get. So I know we are in a fascinating situation because we have this diversity of the system that we call, I think, by lack of imaginations, I mean, mini Neptunes or super Earth, which is actually reflecting on the intrinsic diversity that you have in the formation of the planet. And you can get down to something we know, which is the case of the Earth, which is the green line here, where everybody would agree a planet that could reach this density, that here in that case would match the Earth, it corresponds to an average silicate density, would be qualified as a rocky planet. So the concept of rocky planet is interesting because essentially what you imply here is It's not that there is no atmosphere, there's no gas, or maybe thick atmosphere or thick oceans. It's just that the density is such that you must have a massive amount of heavy element, more heavy than the gas you have in the other one. So that's why we have this kind of concept of rocky planet. And everybody would just accept the fact that, yes, we have found quite some rocky planets, and they are really along this line. And we have found rocky planet in a vast regime of mass above the Earth. I'm pretty sure there are tons below the Earth as well. But the problem is we have not been able to find them yet. So it's very biased. We tend to find the one which is more on the higher side. So this increase here, all the statistic is just has no value at all. So don't try to read the amount here, because it's very, very biased. And depending what you detect, you always find the easy one, the short period ones. But the fact we have already quite substantial high mass, high density planets, I think it's kind of an interesting glimpse into the amount of the one you should get when you go down. And you can practically multiply by many the number just waiting for us to be detected there. So it's a fascinating diagram because it's all a lot of astrophysics here. And you can even dive in and ask the questions, do we have gaps? Do we have the famous valley between different regimes? Do you have sub-regime? Can you identify the effect of post-processing in a way when you have the planet close to the star and the star affecting the nature of the structure of the upper atmosphere? And all this is part of this fascinating diversity that we have to deal with. But they are different planets than the solar system. And whatever we do here, even if you rely to the solar system planet, we have to remind ourselves they are different planets in the solar system. And that's quite an interesting statement to make and to keep repeating. That's why I keep arguing that the fact we detect tons of planets in astrophysics may tell us very little, actually, so far, to the planet of our own solar system. It will only be relevant at the time we'd have really a lot of them that can be compared and try to get this kind of different weighting between the two. Okay, so that's about what we've done. Now, I would like to spend a bit of time on the transit. So as I said, and I really mean it, transit is the worst possible techniques to use for planetary sciences. The chance to pick up a transit for the Earth planet is 0.5%. So it means you need to observe, assuming you have Earth in an Earth configuration and any stars around, you need to observe 200 stars to get them. And then, of course, it's not going to happen. So you may have a chance of maybe 5% to have an Earth system. So you multiply this by 20. So it's not 200 that you need to go, it's 4,000 stars. So the minimum number of stars that you need if you really want seriously to find them would be 10,000. And that's barely what can be done because you need the star to be bright. So this is really to give you an idea. Transit is not good at all. Well, transit being so successful because there is this massive amount of short-lived planets. So that's why people see the transit as the holy techniques right now. But you should have to be really, really aware of that. Now, the other reason why transit is so spectacularly famous now is when you have a transit configurations, then you can learn more than just the density of the planet. You can also assess the atmosphere. And I would like to just spend a bit of time here pointing to facts. First, it's not easy. So if some of you are doing it, you know it's tough. It's not something easy. And it's worse than easy. It's really, really statistically biased. And that's why there are so many discussions right now on the way you deal with the data. And I wanted to convince you what's going on there before, just to show you if you're not really aware of the techniques. When you observe a system, that's the system in transit, and you have a detector behind the telescope. This is what you get. So essentially, this is the signal. It's the amount of light you receive, intensity or flux, depending how you want to scale it, with a different phase, transit, and then secondary eclipses or occultations, depending the wording you want to use. The way we just treat that, I think, is quite interesting because that's what you get. If you look at the occultation phase at that moment, which is very interesting because it tells you the moment when the planet is behind the star, you have this very, very small moment here. The reason why I insist on that, because there's a lot of weight right now on this technology, especially with James Webb Space Telescope, because it's a very interesting moment that time the moment when you don't see the planet. Well, it only works if you have a single planet you want to focus on. If you have many planets, it becomes a bit more complicated. But in case of one planet, you have this information here. So the whole idea here, and it's interesting to reflect on that, is when you measure that moment, that amount of light here, well, practically that corresponds to the amount of light come from the star, right? Now, the massive assumption being made is that sets a 0 point, like a machine, you reset your machine, your scale, that's 0. And anything you would measure out of that moment will tell you something about the planet. Well, technically it's valid. I think anything that comes above that amount is definitely telling you something about the planet. In that case, it's spectacularly telling you that there's a dark sky, dark size, bright size, day side, night side, depending on how you want to do that. Depending on the contrast, it tells you something about the nature of the atmosphere, the circulation element there. So there's a lot of stuff that can be done then, which is quite fascinating. And it even gives you a direct measurements because that corresponds to the way the light is beaming from the planet to you. If you just get the difference here, then if you do that in the far infrared, then it gives you directly the emissivity and then give you the temperature of the planet. So where the first temperature of the planet was measured, 2007, 2008 here. So I think it's interesting to reflect on that because this whole system works on the assumption that the light from the star is a reference. And there are stellar physicists here, solar physicists in the room, so you know it's true. And that's interesting also to weight this element. So in a way it works, it's good. For big planet, short period, fine. But the more you're moving down to longer period, and the more you're moving down to smaller planet, the more it becomes complicated. Just want to alert you on that. So it's great techniques to give you direct information. So, and of course, with that, you get something about the atmosphere. The other way is just measure the transit. So it's for transit spectroscopy. What happened is, of course, you measure essentially the light that doesn't reach your telescope. So that get prevented to reach a telescope. Well, of course, with the solid part of the planet, the solid part will prevent you to do that. But of course, the atmosphere of the planet, depending on the nature of the atmosphere, will do that partially. It's like a sunset or sunrise. So it will affect the color. It would affect, depending of the Rayleigh scattering, depending of the kind of material you have in the atmosphere. You may have some specific wavelength to get entirely absorbed and re-emitted in other wavelengths. So in a way, you will have gaps in your wavelengths absorbed by the atmosphere, where other wavelengths will go just through the atmosphere without being affected. So in a way, you understand the principle that when you have a transit, you have more than just the size of the planet. You have the size of the planet plus the atmosphere. And then this atmosphere can be kind of identified if you play carefully with different wavelengths, because some wavelength will go through or not. So here, I would like to just open a little bit of a Pandora box by showing you two different data, which has been quite famously discussed quite recently. Okay, this is the two objects I'd like to talk about. One, there is a very wonderful WASP-39b, something I know very well. It's part of the WASP program. I was some time ago and detecting a lot of hot Jupiter. This is hot Jupiter on the south of the sun. And the other one is famous K280b. You may remember this. It's a different kind of planet. It's a two Earth radius planet orbiting a late a K-dwarf, and I think the period is something 30 days, something like that. What you see here is exactly the measurements I was talking about. Completely two different planets. So you observe during the transit, you observe the wavelength, and what you see is the amount of light which is being prevented to reach the detector in fractions. So when you look at the Jupiter, the wavelength you were dealing with from the visible to the mid-infrared, they are clearly ups and downs. If you do spectroscopy, it's a spectra. It's pretty clear. Nobody will doubt that. You will see the spectra. And you can identify really on the data where are sitting some specific molecules. And you identify in that case, there are molecules being mentioned here, and you get really a scan of what is the atmosphere of that hot Jupiter. So this is what I would say an amazing use of the transit, because there is no doubt. I think this is what we get. And then we can argue that pretty detailed here, but nobody will challenge that there is no detection of carbon dioxide on that specific line. So that's what I call transit spectroscopy. You see the spectra. And when you see a spectra, it's just... Now, I'll show this one. Same techniques. It's a more challenging one because the planet is smaller, the period is different. So you see the amount of light. I'm sorry, you don't see it very well, but then the effect is very different. Here it's a 2% transit, and you're looking with an effect which is about 40% of this 2%. And here it's not 2%, it's 0.2%, 0.3%, at the 10 lower. You also want to see similar effect, because atmosphere is only a fraction of the planet. Think about the Earth, 6,000, 60 kilometers. So that's the ratio. And usually my ballpark figure when I teach this technique on the principle for people to get feeling of the numbers, they said 60, I get 6,000. So it's 1%. So a transit is 1%. So if you have a transit and you want to see the atmosphere, you have to take 1% of the transit. We can take 2 or 3 in some cases. This is a bit more here because the feature of the atmosphere is more extended. Depends on the temperature, it depends on the weight of the molecule you're dealing with. A lot of elements there, but just to give you a feeling of the number we're talking about. So this is tremendously difficult. And frankly, when you look at the data, which are the black point, do you see a spectra? Really? It's kind of very messy. Okay, this is the way that we challenge here, because to know what you're doing here, you have to rely on a completely different approach. And this here comes the fun. I would say this is a spectroscopic regime. This is a static regime. So you need to infer what you are supposed to have in the data, and you have to look for likely it is that this is matching the data. And you are turning around, playing with different molecules. So you inject molecules, and you try to assume, okay, they must be these molecules. That's my prior. And then I see how likely it is that I get things right. Well, if you do the Bayesian techniques, you know when the data are very poor, you essentially get exactly the prior. Whatever prior you put in. Because there's no constraint on it, which makes sense, it would be Bayesian approach. So you just assess it and depend on what you put in. And the more you have data, the more you should be able to challenging, and then at some point you can adjust it. But that's the whole idea of it. So I just want to alert you, it's a great technique, but we should set the limit at the right level. If you want to do this kind of work, you doing spectroscopy is cool. If you want to do that, you are doing with statistics. And then if you have been attending some of the meetings right now, you know a bit the story here. And people are challenging what has been detected. As we know, the data with the methane, the carbon dioxide have been found. It seems to be kind of okay, which is fascinating because if you assume this is right, the fact there is no ammonia there, and then it's kind of pointing to the fact there must be some big liquid ocean somewhere there, and then you assume there is rocky surface, so it's kind of a new kind of planet we're talking about, and Madhusudan behind this mentioning this kind of high new category of planet, icing planet that is sitting in this regime of super Earth regime. Whether it's right or not, we'll see. I mean, there'll be more data on that, but I want to alert you that is still within the Bayesian regime, and that is challenge. This is still a challenge for. So we can extrapolate how best we can do maybe to look for other molecules, and you know the story about this famous dimethyl sulfide DMS here, which I think is not detected here. Anyway, even if it would be detected, it doesn't mean anything. And I might come back on that a bit later. This connection here I'm making now is to show you this focus from the big planet we have found to the smaller ones, and what it implies in terms of bias, limitations, pre-assumptions. It's all building together. And that is something we have to keep in mind when you start moving to the next frontier, which will be the question of life. And you will see that coming. Okay, now let's go a little bit of something here. Small stars helps. And I'm a great fan of small stars, as you know, and part of a team and led by my Belgian colleagues, trying to use the fact that small stars are cool because then the ratio, if you decrease the size by 10, then you can decrease simply the size of the planet by 10, and you get the same signal. In terms of transit, that's how TRAPPIST was found. And of course, you all know this TRAPPIST system. I think this TRAPPIST system is, in one hand, fascinating, because it's the brightest low-mass stars in the sky, almost in that category. There's not much of this one. There's just maybe a couple of them. But this is very low-mass stars, and it's the brightest one. And could you believe there are 6 planets that, or 7 planets, sorry, there's 7 planets, all aligned with us, with our, in terms of galactic situation. So, my God, it was really a big piece of luck, I would say. This is a gift from the universe here. We've been looking for more of this. We keep looking for more of this. We don't have any others right now like that. We have some maybe with 1, 2 planets, but not this. So it's a unique system right now, fascinating system. And I think it should be also an alert for us. The fact there's only one, despite the fact we're trying to find, we observe quite a lot, it's telling us that it may be not that common. So a piece of luck in the sense that we have this aligned. It's a fascinating system because of the close proximity of all the planets and each other, they are all in resonance. It's a double Laplacian resonance, so which makes a huge effect in terms of transit timing. we can really use that to nail down the mass of the system. And they're all within the mass of the Earth-ish, and all the size of the Earth. So we're really facing here a 7 rocky planet system orbiting a very low mass stars. Of course, in terms of scaling, they would be sitting within the orbit of Mercury, so there's nothing to compare. It's a mini version of the solar system. You know M stars, and they have different stories. The sun was extremely active for about 100 million years, and after, well, kind of the way it is right now, a bit less bright, but a bit like it was right now in terms of activity. It's not the case for M stars. M stars are really active, and even that one keeps being very active. And it's a real challenge. So of course, people are focusing on that system because it's easier. You essentially you have the same sensitivity that for a giant planet. So because of factor 10. So the Earth, if you don't remember the numbers, so Earth and Jupiter is factor 10. It's all factor 10. So Earth and Jupiter is factor 10. Jupiter and the Sun is factor 10. So you can play easily your mathematics here. Remember, the transit goes to the square when you want to scale down. So this is really what is a very interesting topic, but still, we're talking about a different kind of system. So it's great, I'm a great fan of that, but we should be careful not to be obsessed by this. But still, it's an interesting avenue to study, and we still should be diving in on various aspects. First, we should understand better M stars, and if some of you is interested to work on M stars as a topic of study, I think it's a great topic, because it's amazing how little is known on M stars. That is the lost stars in the galaxies, but nobody cares. Of course, they're so boring. Nothing happened. They're just there and they stay forever. There is no evolution, no supernova, nothing there. They don't play a role in the dynamic of the galaxy. Well, they're very numerous, but they don't have a specific role. They're just there, and they're very dim, which doesn't help any observation as well. And they're in infrared, which require kind of different kind of detector, which is not as easy that the CCD detector and the visible. So all this prevented us to understand, and I think this is something that I expect more surprise in the future. Bear in mind they are very different, and that is something we should really have in mind here. Now, how we do with that? So we have no techniques, we have planets, we have 3 planets that have in short periods on low mass stars. So if you use the trick of computing the amount of energy being on the planet and convert that, assuming some assumptions coefficients, even if you take 10%, 20, 100%, that would correspond, and you assume there is an atmosphere, you could find, and you can assume that it could be a planet where if there is water, water could be liquid. So you can assume all of that. Practically, it's nonsense because you know nothing about that. You know whether there's water, you know whether the atmosphere, we just all that level of detail, and even an atmosphere and water is not enough. Look at Venus. Maybe Venus has atmosphere and water. Well, actually, atmosphere right now, but water. Whether there has been water on Venus or never, we don't know. I'm looking for a space mission that's going to land on Venus and study whether we have granite, for example. Granite would be the end game because granite can only be made by water. So we would love to know the rocks of Venus, to know whether there is some evidence that in the past we had water. Let's think about for a minute that we are finding that there had never been water on Venus. Never, ever. Interesting, because water was on Earth, and we never lost water in the beginning. We have the same amount. Mars lost quite some because of the loss of the atmosphere due to the gravity. So clearly, these 2 planets have water. It's obvious, and had it from the beginning. The water, doesn't come only from the outer part of the galaxy. It doesn't work on the isotopes. There may be some, but it's not the answer for the water on the Earth. It's pretty clear right now. But what about Venus? So this is a kind of interesting question. So before people moving into this question of life and the atmosphere, I keep asking very simple question. What do we know about water? Nothing. Nothing. It's fascinating. We don't even know why we have water on Earth right now. So we should reflect a little bit when we talk about life and bring the broad perspective. And I want to explain to you, I think, what I would say not a new community, but there's a refreshing look into all of this, which has been stimulated clearly by this diversity of discovery from planetary science. So it's true to say that Exoplanet has revived the topic. Not by finding any useful data. I think what we have found is not really telling us anything about life at this moment. The only thing that we have done is by pointing the fact we have plenty of planets, and they are different. And then people have to think through that. What does it mean about? And then I will try to go to you what it means in the remaining of the time. Okay, I would like to start with this because that's something that is very popular. This famous blue dot, you recognize it with the awful stray light, poor instrument design. Don't do that if you do that, but they didn't plan it to do this, so it's okay. It was not part of the requirement. The reason why I show that is I think it's really realistic as a community to use that as a goal we have in mind, and we should all have it, not by doing that course with a spacecraft from the solar system looking at the Earth, but seriously doing that, whether it's on the Earth or whether in space, but looking to another system. I think it's really realistic. It has been in many playbook, in many design book, and I think the reason why we're so excited, and it has been going around for many times, if we do that, we should be able to do a spectroscopic analysis of this. And if you do that in the case of the Earth, that's what you get, low resolutions. And I want to show you this because on this information, what is pretty obvious here is, first, you don't need high resolution to do that. Very low resolution would work very well. But look at the wavelength. I mean, this kind of planet, they are only really seriously visible in the infrared. So if you want to make a picture of a planet and you want to see this feature, you have to go in infrared. Of course, we can do also in the visible. It's just you don't see this obvious feature. Then you have to move up the resolutions. You have to deal with the higher contrast. It's possible, but the most natural way to do that is to do that here. So I mentioned this because I think we, as a community, European community, we are extremely well positioned. I'm not saying to do that, but to make serious progress in that direction. I'm a great fan of this machinery. If you've never been to Chile, I mean, just have a look. I mean, I think there is a serious work. Now, I would be in favor of the statements that, yes, we one day will make a picture of a planet like that. And it's going to happen. So when, I don't really know, but I think I don't see any law of physics we're breaking to do that. Okay, what do we do with that? Let's open this. What do we do with that? Let's imagine we do have this. You know, let's just think a little bit through this and give you my reading of this. Well, let's just move to a completely different topic when it comes to biology. You should know that. It's kind of a 101 of biology. But what you may not be familiar with is the tree of life, is a time scale. So hopefully you know, or don't, whatever, just make sure we're on the same level here. This is a tree of life with a time in log scale. So the more you get, you start from here, it's back in time, and you move to there. This is a bit, right? You see all the diversity of the species that you see there, and it's quite interesting to point some element. First, if you ask where we are, maybe it's human, yeah, very late. We see the massive extinctions very well. Spectacular, but not really relevant in terms of life on Earth. There's no impact. I mean, you can lose 80% of life, the massive macroscopic life on Earth. It's not going to change because life actually is this. And think about our ancestors, the bacteria. They are there from the beginning, and they are completely there from the beginning, and they will keep being there until this planet is can still sustain life. So the concept here behind this is life is a very ancient story, and the part of the story is not hiding in the most visible part of it, it's visible in the most invisible part of it, because that's the one that you can connect really much to the very origin. Now, the problem we have in here is we see only the outskirt of this today. And going back to this tree, to the very origin, turned out to be impossible. And people have now agreed that going back, there is Luca, but Luca doesn't mean you go to the very beginning. Luca means it's the last common ancestor. So it's like you take two of you in the room. Where is your common ancestor? You may find, if you live in the Canarias, you may find you have a grandfather, a grand-grandfather here that came, or maybe older, or maybe you're part of the people that were already here before the Spanish came, but they come from Africa, and then still you go back. But there's a limit. You're not going back to the origin of human species. You're just going back to your last common ancestor. So exactly the same problem here. So how do we do that? And I think that people now have done, they're trying to look this in the other direction. It's very interesting questions, because what you find there is essentially the growth of the expansion of life, which when we see it very visible way, only happened in the last 500 million years. It's a Cambrian explosion. It's massive. All the economic creation, amphibians, reptile birds, all what we see now outside, it comes from there. But the life, actually, the origin of life is much more backwards. We kind of agree, I mean, people agree 3.7 billion years ago, there is evidence of life on Earth. There are evidence that they were there. And it may have been a bit earlier, and some people even mentioning it must have happened about 500 million years after the formation of the Earth. Now, when you think about that, you have to reflect on the fact that on that moment on Earth, it was not the Earth that we know. It was a very different Earth. Because this is a very, very singular view of the problem. We call that a kind of a singular positioning, which is the same life. There is no creation of life. Today, no life is created. It's just replicated. So all this is a replication, massive replication process with evolution. That's all what it is. But the onset of life is there. So I'm sorry to disappoint you. You're not a creation. You're just a copy with a bit of evolution, but it's still a copy. Very old copy because our ancestors are there. So that is really the bigger problem we have to deal with, is this fact that when you're dealing with the origin of life, you're really dealing with the origin of life, which is this very moment here. And then the planet Earth was very different. So when you ask yourself, detecting life, you have to consider this time scale. So essentially, for most of the time, life was pretty much invisible on Earth because it didn't really develop in a way that to massively change the structure of the planet. So I have to open a slightly different chapter, which is geophysics. Very geophysics, easy geophysics 101. This is the Earth from a geophysics point of view. Okay, it's a bit like a clock. Here, the way it's being done, it starts at 6 o'clock, and if you have still old-fashioned watches, and you go around, and the reason why I show you that is because we have this idea when we look for life that we have to find Earth and just point and we see water and all that stuff there. And actually, when you look at Earth history, it's a very complex story with a lot of elements going together. There is the astrophysical conditions. This is the way what you're probing when you look at the protoplanetary disk, although you assemble the stuff and what you get. Of course, you are losing a lot of them. The hydrogen and helium we had at the beginning are gone now on Earth, for example. They are, of course, the passive planet, they keep it. Then you have all this carbon-rich falling on the Earth, because remember, the gas, the CO2 gas you have at the beginning, when you go further out, it's not in gaseous form anymore. It's in solid forms. So this is why they are stored. So there's a lot of CO2 carbon stored in the outer parts of the solar system. And most of them, because of the gravitations, because of the evolution of disk, is going to dive into the sun. And on the way, there will be planets. So the Earth is bombarded really by a lot of carbon. So the carbon comes this way, actually, and a lot of the elements coming this way through the fact that this gaseous structure has been moved into a solid structure. So there's all this element here, which is called the deliveries moment, at that moment. And then everything cooled down, and you end up, and that's the planet Earth about after 1 billion years-ish, 500 million years, it's a CO2 atmosphere. So if you ask anybody doing planetary science, what is the most likely atmosphere that we astronomers are going to see on the rocky planet? That would be my bet, CO2, because that's the one you expect, because there's so much of it. So it's a natural production you will have. The very extreme situation is Venus. But Venus has a problem because it's dark, there is a layer that prevents you to really see all what you want. But that's really something that you have to keep in mind. And then there comes the CO2, and then there is the water as well. So water in the case of the Earth was there, so could be detected. If somebody looked at the Earth 3 billion years ago, they would have seen all of that. Well, in theory, because what I'm telling you, we don't have much facts. So the planetary scientists are struggling with this because not much rocks survive that period. For good, because we have the plate tectonics, which is maintaining its level of CO2, at least up to the point we started messing up. But that was really what happened on Earth. And then there is very few rocks that survive. Few of them, like the seal bone, you've heard about this, are telling you something about the situation, but there's very few. There is still the hope that with the global warming, there will be part of the old rocks that we will see that were on the glacier right now, especially in the Greenland. There will be some survivors. Really, you have to think of rock surviving. It means you have a rocks like a boat that never gets subducted and never get down, reprocess, and then out in a volcanic way, outside, reprocess this way. So it's a very fascinating moment because actually the only one that can really tell stories of planetary science are us, astronomers, because we can technically observe a planet in its state. You can even observe a planet which is maintained in this state. Think about lava worlds. They are maintained in this early stage. They never left it because of the intensity of the radiation from the Earth. So what I'm trying to lead right now, to get you with me, is actually don't get obsessed by this life stuff. But ask yourself, what does it mean to have life as a planet? And then there's tons of very, very, very questions about the nature of the material. Is this assumption about carbon-rich true? Well, I think with the lava worlds, we have ways to find out this, the composition of what we're talking about, because the lava, part of it would be in a kind of gaseous forms, and then we can observe them. And there will be some observation already, partially so far. There will be more in the future. So what about the CO2, SO2? I mean, these predictions. So of course, we know after about 1 billion years, there's a prebiotic element, and then we have the Earth as we know it, because it takes a long time. Actually, it's more than 2 billion years. And even the rise of the oxygen, this big oxygenation is being discussed. What exactly was the reason? It's not clear cut. I mean, how it happened and the exact time. They still, if you look at the diagram, you look at the papers, you'll see it's not that obvious that you may believe. Just we have this feeling, or nothing happened, and then big oxygenation, and then okay, it's not exactly like that. It's a bit more complicated, but still. So this is the story. So I just extracted this from a report about my studies, and it's a report that I think is reflecting something interesting. So what a report did is looking at different phases. So the Archean Earth, if you're not familiar with the terminology, is before the prebiotics. It's before it's the Earth before you start having life. So if you want to understand life, you have to understand the Archean world. So I think, to me, we can do progress there. So don't focus on the blue plots. Focus on the Archean. And what can we do there? Well, now it's a challenge. What do we observe? Star, this planet, with 1 billion years old. It's kind of a problem because most of them are rejected from the surveys. Too difficult to do. Just be aware of all this element there because it brings the complete picture there. And I think what they do in the report, they try to project what they think it may look like. Well, that's basically the reflection, the albedo. You can do many ways. The albedo is the way we do that. And I don't want to detail this, whether it's right or wrong. I don't really care. But what is very interesting in this diagram, I think you don't need to be expert in planetary science or spectroscopy to find out that the signal is very different. Look at the Archean, Proterozoic, and whatever. Proterozoic is just the beginning of Earth, the beginning of life that not very massively impacted the system. So my point here I'm making, this is not just 100 centimeters ratios problem. It's a centimeters ratio 1 problem. As soon as you can see that. So if you can see the planet, that's really the problem here, is to deal with the star. If you can remove the star and see the planet, you don't need much because it's a huge effect. It's huge. See this centimeter, 2 or 3, it's enough. So we're not dealing with a third digit or very complicated digit or very, very specific accuracy. It's not an accuracy problem at all. The problem is to see the planet. If you see it, you get it. And that is really the good news because the effect is massive. And that's what we should be looking for right now. That's why I like people that have started to just doing a bit of a poker game and trying to point to some of these poker words and say, can we see evidence of an atmosphere? Whatever it is, I don't really care. Do we see the atmosphere? And there's many ways to do that. And I think this is a correct approach because already answering the fact that there is an atmosphere or not is the first question. And then you can ask yourself, do you see the CO? Do you see the water? And so on and so on and so on. And maybe this will lead at some point to something much more critical here. Okay, now let's go to practically what it means for you if you have proposal? Well, I think this is what we have to solve, and we should bear that in mind. The first one, I think, whatever we do, we should be all frustrated and obsessed by the fact we have not found Venus, Earth, and Mars. It's cool to observe all the target we know. It's cool to do all of that, but don't lose the objective. If we don't get the Venus, Earth, Mars configurations, we're missing completely the point. We have to do that. It requires innovations, new program, and that's one of the programs I'm putting up here with some of my colleagues here. But it's one of the many, and I know there is many more effort in that direction. The second element here, I think, to remember, whether we like it or not, small planets are more geophysical than astronomical. And that is a complete different business. When you talk about mineralogy, you talk about a balance between liquid oceans and atmosphere, it's a complete different. So you cannot solve the problem if you don't build a good network. You have to do with the dynamic of the geophysics. I'm pretty sure none of you have been working with these codes. They're very well known, geophysics community. We have to deal with the astronomical delivery erosions. You may be familiar with that. There's a lot of work when people doing planetary science, cometary science are there about this. And there's a lot of very interesting questions that is there. And of course, you have to deal with the surface chemistry in life, which is chemistry. How far could you read the chemistry equations? It's all about this. You cannot solve the problem if you don't put that into perspective. No, I do claim we can, even with the transit, which is certainly the worst possible techniques, but do something because you have a great machine right now. So let's do it. But we should remind ourselves the limitation and really be very aware of that. So for you, I'm familiar, this is the numbers we deal with that. Transit is 1%, Neptune is 0.1%, Earth is 0.01%. So that's the true number you can come up on a solar cluster, right? So get an atmosphere on Jupiter, 10 to the minus 4. Could be done from the ground if you're really good. Easy to space, easy. And there will be more, and there will be Ariel, there will be a lot of stuff. So there's a lot to do here. And I think this would be really changing. After Ariel and after all the observations being done, I think there will be a complete new revival of this hot Jupiter understanding. Hopefully we understand better the formation of hot Jupiter. Second one is James Webb Space Telescope give you access to 10⁻⁵. I think it has been done. It's difficult, it's possible. If you stay on the Neptune, it's okay. When you go down, it becomes more challenging. But this is the realm of, I think, the most exciting bit. It's between spectroscopy and Bayesian statistics here. Hopefully, they will get some better understanding. The more we observe, more data, we should be able to get that. Earth, going to Earth, is 10 to minus 6, no way. I think this is the opening to endless discussions and a lot of false alarm here. So I think we're not ready for Earth right now with transit. It's okay. I think we have plenty of other planets, very interesting. And that is opening the big questions. Do we really need an Earth to understand the formation of a system like the Earth? Maybe we can deal with something much bigger. It will tell you a similar story. So I think we may end up in a situation where the understanding of the Earth formation will come as a byproduct when we will understand already the huge diversity we have there. So I would not give up. Now, I still believe that despite I'm a great fan of all this result and data being produced right now, we should make sure we're not doing only transit. And I keep advocating, and I know here you are working on other aspects, but it's not the case everywhere, especially for the young generations. Have a look about what comes next. And we will have to move to direct imaging. There is no way. Transit is so frustrating here. And we have to develop a complete new approach here. Aware of the challenges. As I said, 10 to the minus 6 is what you deal in infrared thermal object, which has to be done from space. If you want to stay on the ground, 10 to the minus 10, assuming you are dealing with the atmosphere, which may be a challenge at that contrast level. Now, we may need to team up. Again, it's always a call for international community work, like the ELT's tremendous success. I'm really looking forward what the ELT would do, but we need more than the ELT, I think, and that we need to plan a little bit further. It's a big change. I think this field of exoplanet was in the shadow of the cosmology for quite long, in the sense that they have been using the amazing development of technology, which has been done for the purpose of the deep universe, for good reason, because I'm a great fan of the deep universe. But I thought we're coming to a new moment where we can shine a bit more and ask the questions, if you have to design a machinery just for us, in a way, optimized for us, that can also do something else, where can we go? And that is kind of process right now into the community. I still believe the community is still too young to be able to go that level. compared to the cosmological community. But if you keep doing good like that, I think at some point it will come. Now, this is a slide I stole to my colleague Sasha. Sasha is trying to project himself in a deep future, far future. So this is a bit what we can do right now. So expectations, can we really do something? And you see that there's still this ELT with some Earth-sized planet, we can do something. And that's true, because when you look on the paper, on the design, first of the telescope, the 39-meter diameter was on force and maintained with the vision that they may be the only size we need, the minimum size to see a planet. But my understanding, talking with the people that design instrument for the LT, there is only one stars where we may be able to see something with a direct imaging, which is Proxima Centauri. Okay, there are 2 planets there, so it would be cool already to do it. We're very happy to see that, really, frankly. So, but if you really want to be more systematic, I think we may have to go to space. And then it's another kind of territory. And although we have been facing a bit of challenges, both because of all this geopolitical conflicts between the big countries right now, and also a kind of a change of turn into the strategy of the fundings, especially in US. So we have to see how it goes. Sooner or later it will come. We need to think about the flagship. James Webb is limited, clearly, to do that. And in the imaging capability of James Webb is very limited. Okay, now what I would advocate as a final remark here, I don't know if you pay attention, but I use a couple of words that is completely unusual, usually in astrophysics, what I call the comfort zone. I use geophysics, I use chemistry, I use mineralogy, all this stuff. And I think this is something I personally went through a couple of years ago. I personally realized that I think I was really interested about that topic for life, but I was not seriously enough interested as a scientist. I was more interested to talk about that in front of the public, which is cool. But if you really want to make progress, you have to change the mindset. And that's the reason why I've been involved since about 10 years now. I've changed the focus of my work, because I think we have to change the mindset in a positive sense, not forcing anybody, but offering opportunities, which is a bit different than the one we have. I want to show a diagram that I use sometimes. It's a bit complicated, but it's the good approach we had with the Neighborhood Center in Cambridge, and I kind of propagate to other places and know in ETH as well. Is essentially the problem of life. It's a combination of 3 elements have to be put together. And you have the elements of chemistry, practically, and there has been progress on chemistry of life, especially life as we know it, the one we know, because it's the one we can deconstruct or reconstruct. There are the questions about the planet itself. The chemistry of life happens on the planet. It's not in the lab of a chemist. So the chemist is the physics of the planet. So you have to include the planet. And I think it's great, because you can imagine that depending on the chemistry of the planet, there may be different optimizations for the production of life. Or maybe life has only one way to go. And then it means you have to restrict the planet diversity. Nobody knows about this right now. But that's something to bear in mind. And of course, there is this diversity, which is the exoplanet part of it. The 3 of them together, they have a lot of link. The link between the planetology and earth science, chemistry, and then planetary atmosphere studies there. So they all have link, and they all looking from different angles. The key here is essentially 3 problems that we have to solve. The first one is, how do we make the molecular architecture of life? Do we have other ways to do that? Let's find out how. And one day people will say, I cracked the code. I know to make life from scratch within these conditions. It has never been made. There have been progress, and they are very interesting, but we never made the wood show, which is to produce a chemical structure which is evolving, essentially, and self-replicating, and believe that it looks like kind of something alive. What does it mean, life, for us? In terms of detections, biomarkers, or ecology of the planet, which means we don't focus on the biomarkers, but we focus on the global systemic element of the planet. Water, planetary evolutions, temperature, whatever, chemistry, the whole systems, the whole planet as a system. What does it mean? And we can really do that without focusing on that. And of course, the questions of the co-evolution of life environments. We know that planet has been very different in the past. past. We even have experienced a very dramatic events called the snowball Earth. There's more and more evidence that happened. And it's kind of magical to realize that we went out of it, possibly thanks to volcanic activities. So all these elements are playing a role, and maybe there is a specific ecological niches that you have to think about it. There are specific conditions on the planet to make it happening. This is why we're so obsessed by Mars, because Mars, we guess, if you go back in the first billion years, may have been very similar to the Earth-ish, because the chemistry of life, chemistry of the planet Mars is not the same. So there is some differences. That's why the claim is very exciting, recent claim, that they may have some traces of bacterial activity on the rocks. Of course, it's kind of easy claim because anytime they see a structure that cannot be made by the planet itself, they identify this as being a trace of life. The only way to find out would be to bring back the rocks and to study the isotopes, because we know that life, by the catalysis mechanism to make life happening, which is a chemistry going on. I mean, when you cook, you have to heat or you have to shake if you do mayonnaise. But you have to do something, right? You have to break the barrier of potential. Well, chemistry is what catalysis is doing. That's what life is doing. That's what the ATP is doing every day in your body, every time, every milliseconds or whatever, producing this, breaking this energy, making this energy. So this is the key here. And by doing that, you change the isotopes because some are more naturally prefer, and everybody know the carbon-14, for example. Which is the way we can trace it back, because carbon-14, the production of the carbon, the wood carbon on planet Earth by now is processed by life. There is not a single carbon which is not processed, except that it can dig out of the crust, out of the volcano, but all the rest is processed by life. So the carbon, you use it as a process by life and have a slight difference into the isotopes, and you use it to time when life doesn't affect the carbon anymore, when you're recycling, and that gives you the time of the carbon-14. So everything can be done at the isotopes, but you have to bring it back. So the ultimate proof to me that there may have been life on Mars will come the day when we have people to explore Mars and bring back enough element to study the isotopes and find there are some imbalance that doesn't make sense by the natural structure of the planet. And that's one way to find out. Whether there is actual life on Mars, I don't think it's the prospect, but there are waters, who knows? But the idea that there may have been the beginning of life on planet Mars is not crazy, I think. And that opened the last chapter I would like to share with you. I quite often get asked when you think about life in the universe, I say, look, chemistry should be the same everywhere. So I can't believe that chemistry doesn't try to make life every time. There's the statement that life is written in the fabric, the universe made by the bird. So the whole idea of life as a natural result of the universe, like the star as a natural result of the universe, not given. They have a big bang. It's a very boring moment. Nothing happened much because we have the stars. The fact of the stars making the elements, and the elements are doing the chemistry because they are planet and atmosphere. Then you can have a liquid, and then you can do the chemistry. So you see, it's not a given story, and it happens because the conditions are there. So if we had a life on that planet, it must have happened anywhere. And I pretty much believe that they are the right concept of conditions. Life happens, but whether life stays, that's another story, and that makes us maybe very exceptional in the sense that the condition for life has been very long on that planet, never failed, like it did on Venus or it did on Mars. And that may be why at the end we have some human species that just by the purpose of the evolutions have this consciousness level and are able to trace back the functioning of the universe. So I think this whole story about having life everywhere and having life able to build up a civilization is very different. I think I tend to believe the process of life is quite universal. That's why we think we should be able to find it, I think find out. Whether it leads to many evolutions and many enough time to have consciousness and to have a civilization level, maybe not. And maybe we are the only aware of the universe in these galaxies. I don't know about the other galaxies. Let's do it with these galaxies. Okay, I will leave you with that. Thank you.
time for questions. But
Thanks a lot for the beautiful talk. I think the path forward that you have sketched for the next, let's say, 20, 30 years is fairly clear on the observational side, and looking forward to seeing the results. I wanted to ask you about the observation, the theory and modeling side. And what's your opinion about what we should focus on in the next, 10, 20 years? Whether we should, I don't know, try to challenge the solar system formation and try to explain what is out there, or should we just keep on going and cross fingers that the next observation campaigns will reveal the solar system planet-like? And like, in your opinion, what are the most urgent questions that you'd like theorists to focus on in the next, let's say, 5, 10 years?
Well, it's a very difficult question. So thank you. Well, first, I would say that I think the overall picture that the theory of planetary formations is giving us is pretty good in a way, because there's a lot of elements that we can refer to and match. The global picture is pretty good. It's a bit like the weather. So I think it's good. We understand the Navier-Stokes equations, we understand the global pattern, and you can work through that, and that's fine. The problem of theory comes in when you want to be more local and specifics. And the problem you have to face is, at some point, it's a completely different story about talking about the structure of a rocky planet, the dynamics between the surface of a planet and the atmosphere, or the formation of a giant planet, or the early stage of a protoplanetary disk. So I think these are very different topics. And right now, it's possible a big challenge for theorists, because either they focus on their own narrow-minded approach and they go in more detail with limited data, we have to admit. In some cases, there's quite a lot, and protoplanetary disk, there's a lot and a lot more coming. But or they try to connect outside the comfort zone, and they start asking you questions about, if you do protoplanetary disk, for example, it's about what could you really say about the solids. I mentioned the solids because it's a big problem usually to bring those together. And how far could you say about the mineralogy of the solids? How far could you provide a better picture of the evolution of the minerals? And then you're entering a complete different domain, which is completely out of the comfort zone, which is the mineralogy, gold mineralogy, all this. So that is the challenge of the theory, because the planetary science has many scales that is quite unusual for people doing astrophysics. If you do cosmology, well, it's easy. 7 equations, seven parameters to find. That's it. Well, it doesn't mean you understand dark matter, dark energy, but at least we can play with this different way, and you can play and see what is changing this parameter. You see what it looks like. In the case of the planetary sciences, there is billions of parameters you can change really together. So theory will have to find a way to navigate into that. You have to stay away from weather prediction, because it depends so much on the local conditions. But I think you can say a lot about the global pattern, but you may want to explore maybe the connections between different fields, which is not happening right now. Possibly because of lack of curriculum, because of some biases, because also publication challenges. As soon as you get out of the usual, fixing remit of a journal, it's become difficult. So they are editors of journal, be aware of that. Don't get obsessed sometimes. And also maybe by lack of innovations, if you're referee of proposal, don't be too tough with people that exploring a bit innovation approach. Sometimes people prefer to stick on something they know. So this is all about progress. And there will be some progress, but at the end, I think it's almost an unsolvable problem if you want to solve it completely. Like the idea, predicting what a planetary system will be. I think this is nonsense to me. I mean, it's like predicting the weather in 6 months in La Laguna at that time. You can have an idea about how it would be, but you cannot predict exactly whether it will be sunny or rainy, right? Depends on the time. So it's just my point. It doesn't mean you don't predict globally the overall temperature and the conditions there, but the specifics would be difficult. So I think we should get rid of this. And I think always a bit worry about people trying to be too much specifics into predicting what a planet should be like according to some formation scenarios. I think there's so much assumption behind. So that would be a challenge for the future.
Okay.
That's my view, but I'm not doing theory, so I have an easy game here answering you.
Great, thanks. Just a very quick question. Out of curiosity, in your very personal opinion, what do you expect the next Nobel Prize in exoplanet to be? I mean, like what?
So the next
what?
Next
What do you expect, like the next major discovery in exoplanet?
major discoveries.
Like be awarded with the next Nobel Prize.
So like that.
Sorry.
Well, I will not try to understand the Nobel committees. Nobody understands them. Even them, I'm not sure they understand what they're doing. So it's difficult. Okay, let's do this following. We have had a very extraordinary moment where nothing was known. So everyone doing a little bit of something would be a breakthrough. So I had an easy game because detecting hot Jupiter, frankly, it's easy. I mean, you can even do that at the masterwork right now, master program. So it was easy because nobody had done that before. So of course, the more we know, the more bigger the community, the more details are going on. So the more it's difficult to make this doing one thing is going to change the whole world. Now, I still believe that whatever we do, science is driven by data. So whatever you do, data is the leading element, except if you do foundation theory of physics, but it's data telling you what is going to happen. So let's just look at what are the data coming. And there are an amazing number of data going to come. There has been a successful, an amazing number of instruments being developed on big telescopes, smaller surveys, space mission. I don't want to make a list because I don't want anyone to complain, oh, you didn't mention my equipment here. But when you look at how many equipment is not being designed right now, has been built and are really being installed, it's amazing. So for any of them, they will have a niche to provide amazing discoveries. So going through all of them, at some point, will give you kind of a picture. So you mean improving some detection, detecting some new feature on some new planets, finding out maybe some specific molecules that have an impact on the formation of the planet, and so on and so on. So I think this will go this way. My usually approach in exoplanet science is because of this bias we have a completely empty territory. If you want to deal with the questions, how do we connect with the solar system? It's empty. Nobody has done anything right now. For any work in that direction may lead to breakthrough.
Okay, thank you so much.
Well, I really enjoyed your talk because I don't know enough about it. I still don't know enough about it, but thank you very much anyway. In one sense, searching for life is actually more typical than you might have thought, because astronomy has always been an observationally led discipline. Only when you find it, suddenly you realize, oh yes, of course it was like that. Astronomy is very good at post-diction. It's always been better at post-diction than prediction. And that is slightly different, apart from Einstein. But much of astrophysics has been driven by observations. And I can't see any reason why this should not be the same. The more you manage to observe, the better chance you have of finding it. It's pretty obvious. But I think that will have to be the way.
Yeah, I would agree. So to me, there's two elements to astrophysics. There's using the universe as a lab. So it's an amazing lab because you can see things you cannot see in any best lab on Earth. It goes from gravity, you can time, and all some extreme event and density or whatever. So this is one element. So it's the ultimate lab to test the law of physics, and it always been, and it will still be for a long time because there's nothing can beat the universe. The other one is just understanding the universe as an object that goes what is in the universe, and that then lead to the question of life and matter or dark energy, and then to understand what it is in terms of object. So clearly the observations here, the challenge here is we know life as we know it right now, but nobody understand if this is a kind of a minimum, minimum of energy processed by the chemistry. Is it the only way to make it? Or if you change the chemist by changing the planet composition, you will have another kind of way to do life as well. And that is completely open. Now, it may well be that we are going to miss most of the discovery life because we don't just know how to recognize it. That would be one big challenge. But people is aware of that. And there's always a hope when you understand life, and it will happen, to play with that and try to explore, okay, if I change this parameter, do I still have something, or do I create another structure that also could evolve and is sustainable? I just don't know. And that's part of the process that people are doing right now. But you're right, it's about observation at the end.
Thanks. Great talk.
Thank you, Ralph.
High contrast imaging. So you said 10 to the minus 10, 10 to the minus 6. Just to recall here that if we go for a brown dwarf of 1,000 Kelvin, it's 10 to the minus 4 only in the mid infrared. So I think that's the niche that you could add in your next talk.
No, I agree with that. That's a low mass opportunity. So yeah, the reason why I'm more careful with the low mass opportunity is this TRAPPIST story doesn't point to a massive number of planets now on these low mass stars. And I cannot say this is the way to go. Well, it works down to the early M stars. Clearly, there is a lot number, but after there's a drop. Now, there are theoretical reasons why you may have a drop, actually, and forming the planet. Now, of course, you can argue, well, let's go smaller. But I'm not interested about Mars, because Mars is too small for life. So don't go too small.
Great talk. You have a slide where you had the European ELT saying a few Earth-like planets, and then habitable worlds and saying dozens. I want to understand the limitation from one to the other in the sense of, well, there is more photons on the European ELT than on habitable worlds.
Yes.
The good thing of habitable worlds is that in space. Are we saying that as you improve adaptive optics with the European ELT detectors, adaptive optics, and you will be able to get to dozens of Earth-like planets with the ELT, or is there a fundamental limitation?
Okay, it's a very good question. So actually, you're right. Depends how you play the parameters. First instance, the size of the telescope is the first element, for sure. That there's no doubt of that. Now, a planet is bright. It's not like cosmology. We don't fighting about very dim objects. A planet is rather bright, actually, when you really work to the magnitude of a planet. The problem of the planet is not because it's bright, it's because it's next to an even brightest object. So the question is, what is the best combination to observe an object next to something very bright? And then the size of the telescope matters, provided that the optics is able to just get rid of it. Technically, you could use a smaller telescopes if you're good at removing the bright stars. And that's the trick here. And then the big problem we have on Earth is the atmosphere, because the atmosphere brings these intrinsic limitations you have into it. So you have to really froze the atmosphere to such a level to be able to use the whole, whatever coronagraphic technique you think about it. That makes it extremely difficult. And currently, my understanding, it's if you account for the best ever system, it may still not be possible, because the trick on the ground is to use the high resolutions, because high resolution go through the atmosphere in a way, because you can identify the molecules. So the best bet right now is really to go to space. Now, there's a big debate whether we have to go to the visible, on the infrared, or mid-infrared. It's not a serious debate. It's just a diplomatic debate because there is more interest by the community of users of such equipment, and it's not only the people who want to do planet research, to have a machine that is smaller and moving more on the visible than going in a mid-infrared. Mid-infrared is really more focusing for us, and it's still difficult in terms of detector. So we're still at the limit. So whether it's doable in terms of technology, I'm not even sure right now it's possible to do that. But surprise may come. I keep telling one day, maybe the electronic would have been so much progress that we will operate the visible telescope like a radio telescope. And we can record with an atomic clock the time of the arriving photons in the visible. Then you have a visible telescope the size of the Earth. If you combine hundreds of telescopes on the Earth, and that's a done deal, you're done essentially here. You don't need big telescopes because again, it's bright. So a small telescope with an amazing way to remove the star would be enough. I don't know the number, but that's really what it is.
Good.
Thank you very much. I have actually a question that goes a little bit into the direction of the previous question, but turns it around and looks at the stars. So you mentioned before, look at M dwarfs. M dwarfs, they are very unexplored because they are very boring in the sense of they're not doing a lot. If by whatever magic you wouldn't have like observational constraints, at what star, what type of star would you look at for the best chances of finding an interesting exoplanet, doing interesting astrochemistry, for example? And related to that, what advances in stellar physics, stellar astrophysics, you think are very important to advance the field in exoplanets as well?
Okay, so there's different way to answer these questions. I'm not saying my answer is the only one, but I will give you mine right now because what I'm doing right now. There is one fact that everybody would agree. If you assume that the limiting factor right now is a star, the best star we know is the sun. So I would observe a star as close as possible to the sun. That would be. But there is another approach in terms of sensitivity. There is plenty of good reason to use small mass stars for the reason that Rafa explained, all this what I explained. So there is another argument, which is not the practical argument of optimization of the possibility of observe them. So that's the angle of approach, which is absolutely valid. But the challenge there is for the community doing that to admit they have to spend more time on the star. They cannot use what we know on the sun is useless for that kind of stars. So that's the big challenge. So right now we are facing this lack of work because nobody has done any work. I mean, it's amazing. You look at M stars. I mean, there's so few publications on M stars as an object of study. It's kind of a community that disappeared. They appeared at some point in the 60s and then went away. And then the brown dwarf went the focus, of course. The brown dwarf, very interesting object, but it's brown dwarf. It's not M stars. Usually they are rejected. It's boring M stars.
Thank you very much for your talk. I would like to ask something more from an observational point of view. So what do you think that taking into account the current observational constraints that we have, given the facilities that we can access and the space telescopes that we are using right now, what do you think are the best observational parameters or even spectral features that we could use as tracers of planet formation and evolution?
Well, I would really love to see more spectra of atmosphere of planets. When I say spectra, I mean it. I don't want to be seeing only Bayesian analysis of possible detections of molecules because that would be so difficult to extract. So there is a regime where clearly between this kind of super Earth regime and then the Jupiter, there's a full range of objects that we need to understand and to understand what are the molecules there, what are the atmosphere, because that is a kind of a way to do that. So there is another topic, which is to me very interesting as well. I didn't talk about it. It's a white dwarf. I don't know if some of you are working with white dwarf. wide dwarf is interesting. It gives you a very interesting angle, a kind of end product, because the white dwarf, I mean, the polluted white dwarf are clearly a sign of the mineralogy of the planet that has been orbiting this system. And my last recall of the last seminar I was listening on that is they find something very consistent of something we have in the solar system. But I think it's very good because it means we can still use a planetary model of rocky planet as we know them on the solar system and trying to extrapolate them into maybe a slightly bigger, maybe different, maybe with a bigger atmosphere. So to me, there is really a whole new field here. So I would advocate, don't get obsessed by this Earth and super Earth and life. Just leave that aside and leave that maybe for your press communication and stuff like that. But don't try to argue in the paper. It's just a source of confusions, and a lot of people will just react, overreact, because it doesn't make any sense right now. So that would be my advice. So a lot of target you can do, and TESS is providing quite a lot of them. Plato should also bring some more object, more on the bright side, but there are some area that they would bring as well. So I think I can imagine in the next 10 years, we will have a very good understanding of any transiting planet within maybe 2-3 months of period for anything up to magnitude 12. And we should really have that, which is an amazing survey. Of course, it will be just a fraction of the planet, but that would serve as an amazing series of targets. So you have plenty of target to pick.
Okay, thank you. And if we manage to get that real spectra with enough signal for these kind of planets, what specific spectral feature will you be looking for to make a one-to-one relation between what you see in an exoplanet atmosphere and how it formed?
Well, then I would start talking with the theory, and I would ask them, look, we found that kind of molecule. Doesn't make sense, because that, if you look at this, it should only be visible at that stage of the planetary disk. How do you come to have that much amount? So what does it mean on the planet? So what can you guess the structure of the planet? Could you say that there is some kind of rocky core or huge rocky core on the basis of the chemistry? So they're really connecting to the theory and connecting to the people doing detailed chemical model of the atmosphere. And again, talk to the planetary scientists, because they have this knowledge and they have these tools to do that. It will be maybe more complicated. And that is the same story that happened 30 years ago. When we had the first hot Jupiter, I remember the first discussion we had with the people that used to study Jupiter. We had a non-dialogue because they were talking on the third digit about whatever numbers, and we're talking about the first digit and barely with just even the fraction because of the sign I. Because we're trying to get something from them, and we're trying to show them the diversity has to be in a way considered by them. So it took some time to quite often the new generations of scientists trying to understand that and build up the more consistent dialogue. So this really where is the trick. I think I would really advocate for more dialogue between slightly different fields. Try to invite, I don't know if you do, a geophysicist, or you must have people coming for the volcano here. I'm sure there's plenty of people that would love to come to give you a talk about the volcano, the mineralogy of volcanoes. And this is quite interesting, because that is really what we're talking about the planet. A volcano give you something out what is inside.
Thank you very much.
Thank you, Didier. I don't know if you can answer this question, but in any case, I'm going to ask you.
Oh my God.
What do you expect of ARPS 3?
Oh, that's an easy. A lot.
No, I mean, in relationship with the...
Okay,
with the
well, ARPS 3, ARPS 3 is built on a simple idea. First idea is we have the equipment that has a sensitivity to detect small signal, some small radio velocity signal. There are others like that. There are other apps in a way. Well, this one is just the last versions. We're trying to incorporate a lot of lessons learned by Espresso, typically, and demonstrate this. So there's really a lot of evidence right now on the machinery is capable to reach an accuracy that is able to detect a planet like the Earth. So really, and everybody now understand the problem is not anymore the machinery, it's trying to get rid of the intrinsic structure of the variations of the atmosphere. I use structure because it's not a noise, it's a structure. And the kind of way to do that, there's many ways to do that. One of them is, well, best data possible, I mean, highest signal to noise ratio. It's the first element. The second one, as much data as you can get. Essentially means data every day. And that's what ARPS-3 is doing. So it's implementing this full process that is collecting data with the highest possible signal-to-noise ratio, which means we cap to very bright stars. There is enough. There's about 1,000 stars, almost like the sun, that we know nothing about the planet on this, and then brighter than 8th magnitude. 1,000. And there's maybe 10%. There's a hint about Jupiter and stuff like that. So it's very fascinating to realize that we don't know the nearby stars there, because the transit is not finding these objects. The transit is focusing on farther out objects. And the radiosity survey been focusing on few of the bright ones, and because of the lack of this time, telescope time. So that's really this idea. Now, my expectation is we're going to demonstrate that we can deal with the noise of the structure of the stars, that the approach is right. And I hope that this will stimulate then a completely new way of developing survey in radial velocity. And my hope is after ARPS-3, there will be 10 times more ARPS-3, because that's the only way that we can find an Earth planet as of today. And that's the only way to do it. But I want to demonstrate it works. And until we demonstrate it works, it's just words. So that's my hope. Let's meet in 10 years.
Thank you for your talk. My question is, now I understand that the obstacle to detect the signal of the life signal, let's say, on an exoplanet is the problem of the star, because the signal is 10 to the minus 5, 10 to the minus 6. Yeah. Let's forget about the star, even the sun, even M dwarf, even ultra cool dwarfs. How about, what's your opinion to detect live signals on free-floating planets? We haven't found any rocky free-floating planet, but on those still gaseous.
For me, the dream scenarios is having one free-floating planet crossing somewhere not far from the solar system. Because then we could go.
So you think there is a...
No, because I went to the math, and I think the chance is 1 over 1 billion years. I'm so sad.
But we don't necessarily need free-floating planets that's close, right?
Okay, so what you say is we observe a free-floating planet and we just try to see what we could get from the spectra. Yeah. I didn't really went to the math. It would be very cold, because nothing, so you would have only the temperature from the radioactive radiation. So the temperature would be close to Pluto, right? So to detect it, it means not much photons. How would you just see it? It's very cold.
Some of them are a little bit warm, like 500K, 400K, something like that.
500K, they would be very young then.
Massive. 10 Jupiter mass. Maybe they are alive floating in their atmosphere.
You should maybe try to see whether there is I've no idea. I mean, frankly, I have no idea. So I'm not against it. I think there's clearly a fact that there must be plenty, but this is so empty. So actually, my hope having one closer and we can just go for that. So I'm very interested also about objects that come from other systems that we have no clearly comet that come from other places. To study them, to be able to study one of them much better. Not as an archetype of a spacecraft visiting the system. So this is a big joke. There will be only 1 people on Earth believing this. What I'm talking about. But it's very interesting to just probe the mineralogy, what we're going to find here. And because there must be plenty of stuff is moving around between the stars. And that is something that will be a new topic for astronomy. I think with Rubin telescopes and LSST can find them and Rubin can follow them. So that would be an amazing pair. I mean, that would be a great topic actually for PhD. I'm trying to just find out what is the sensitivity with LSST to find more of these, and then to follow them up with the Rubin. So maybe it would answer partially your problem. But yeah, cool. More planet, I'm happy.
Okay. We don't have more time, so we thank again Didier. Please.
Good. Okay. So,